Problem 1. In our class, the concept of true stress and engineering stress has been introduced. From the concept that the volume of the sample before stretching equals to the volume of the sample after stretching, show that the true stress is equal to engineering stress times 1 plus epsilon, where the epsilon is the elongation strength. First of all, we should draw the initial diagram and after stretching diagram as shown. Moreover, we suppose that the cross-section area of initial diagram is A0 and the cross-section area of after stretching diagram is A. And then we suppose the length of initial diagram to be L0 and the length of after stretching diagram will be L. And L is equal to L0 plus delta L. Because the proposition of the problem, volume of the sample before stretching should be equal to the value of sample after stretching. So A0 times L0 is equal to A times L or A times L0 plus delta L. And then we can use algebraic manipulation to get A is equal to A0 L0 divided by L0 plus delta L. Finally, we consider the two states. Two states is equal to force divided by area, and then we substitute A is equal to this thing. So, two states is equal to F divided by A0 L0 divided by L0 plus delta L. And then we can use algebraic manipulation to get this. Moreover, consider L0 plus delta L divided by L0 is equal to 1 plus delta L divided by L0. But epsilon is equal to the elongation strength. So epsilon is equal to delta L divided by L0. So this one is equal to 1 plus epsilon. Moreover, F divided by A0 is the engineering stress. So we can conclude that true stress is equal to engineering stress times 1 plus epsilon as designed.
The question number 2. A sculpture weighing 10,000 Newton rests on a horizontal surface at the top of a 6 meter tall vertical pillar. Figure 1. The pillar's cross-sectional area is 0.2 meters square meters and it is made of granite with a mass of density of 2,700 kg per meter power 3. Find the compressive stress at the cross-section located 3 meters below of the top of pillar and the value of the compressive strength of the top 3 meter segment of the pillar. Young's modulus of granite is 4.5 times 10 power 10 Pascal. So first we have to find the internal load and we can find by mg, and all of mg is the mass of the sculpt plus the mass of this rod and this rod we can find the mass by using rho v is equal to mass, and we got it. This is the mass, and so total mass is 26,000 and 200. And next is stress. We can find stress by using this formula. So we get the stress is 131 kilopascal. And next is finding the strain. And strain, we use this formula to calculate. So formula is Young modulus is equal to stress divided by strain. So strain is equals to stress divided by Young modulus, and this is the answer.
Problem number 7. The stress strain graph for metal wire is shown in the figure 7. The wire has a diameter of 0.84 mm and a natural length of 3.5 meter. Use the graph to determine the Young modulus of the wire. The extension of the wire when the stress is 0.6 gigapascal, the force which causes the wire to break, and the energy stored when the wire has a stress of 0.6 gigapascal. I will give this one is A, B, and C. From A to B is the elastic region, and point C is the used. Number 1, they want to find Young modulus, and from the formula, Young modulus equal to stress over strain. And from the graph, you will know that the stress is 1.2 gigapascal and strain is 8 times 10 to the power of negative 3. And we calculate it and then get 150 gigapascal. Number 2, they want to find the extension, so they want to find delta L. When the stress is 0.6 gigapascal, the strain is 4 times 10 to the power of negative 3. So the strain equal to delta L over L, 4 times 10 to the power of negative 3 equal to, and L is equal to 3.5. Then we get delta L equal to 1.4 centimeter. Number 3, they want to find the force when it breaks. So when it breaks, you should know the stress of when it breaks, and the stress equal to stress at point C equal to 1.52 gigapascal. times 10 to the power of 9, and we know that the diameter is 0.84, so the radius is 1.42 millimeter. And we calculate it and we get F equal to 840 Newton. And the last one, they want to find the energy stored when the wire has a stress of 0.6 gigapascal. So as you can see that area under the graph is stress times strain, and stress is F over A times delta L over L. F times delta L equal to area times AL, and we get the energy is equal to area times A times L. So they want to find the energy when the stress is 0.6, so it's this point, and the area under the graph is triangle, so 1 over 2 times 4 times 0.6 times 10 to the power of 9, and the area of the cross section is pi times 0.42 times 10 to the power of negative t, and then square and times 3.5 meter, and you will get 2.3 Joule.